Hi, my name is Mark Smithson. I'm an author on the recent opinion article, Transmissible Viral Vaccines, with Jim Bull and Scott Newsmer. Most of us worry about catching colds and contagious illnesses from others. But what if vaccines against contagious diseases could be caught and transmitted in the same way? In order to transmit, the vaccines would need to be live and capable of replicating. Although transmissible vaccines sound like something out of a science fiction novel, most vaccines in use, and even more being planned, are live, capable of replication, and possibly capable of transmission. Genetic engineering is advancing so fast that we may soon be able to create transmissible vaccines easily. The potential benefits of transmissible vaccines are enormous, but there are some safety concerns that need to be figured out before their successful implementation. Transmissible vaccines could aid the fight against infectious disease in wildlife populations, and use in humans may be warranted for populations that are hard to reach or for epidemics that are uncontrollable by direct vaccination. However, using transmissible vaccines could be dangerous, mainly because vaccines with the potential to spread through a host population also have the potential to revert back to the disease. In this video that accompanies our paper, we introduce the two main designs of vaccines that are currently in use and have potential to transmit. Then we discuss the epidemiological and evolutionary challenges facing each design. There are two main vaccine designs currently in use with potential to transmit: live attenuated vaccines and recombinant vector vaccines. Live attenuated vaccines are mutated, genetically weakened versions of the disease they are designed to protect against. The idea is that they create a subdued infection that is otherwise similar to the disease and elicits immunity just as if you were infected by the disease, but they don't grow well enough in you to make you sick. Historically, they've been created by growing the disease virus in unfavorable environments such as high temperatures, novel hosts, or novel host cells. Adaptation to the new environments reduces viral growth rates in the natural host so that the vaccines impart immunity without causing disease symptoms. Currently, live attenuated vaccines are used in the fight against measles, polio, mumps, rubella, influenza, chickenpox, and many other viral diseases. For most of those live vaccines, transmission has not been reported or is extremely rare. However, transmission is well documented for human oral polio vaccines and vaccines against myxomavirus in rabbits. The other main type of vaccine with the potential to transmit is a recombinant vector vaccine, which combines two viral genomes. Here we focus on recombinant vector vaccines that engineer genes from wild-type disease viruses into benign viruses. The benign virus is otherwise intact, so it serves as a vector for the transmission of the disease antigen. When delivered to the host, the benign virus multiplies and the host builds immunity against the disease antigens that are encoded in the vaccine. Some viruses being developed as possible vectors, against Ebola for example, are cytomegalovirus and vesicular stomatitis virus. Recombinant vector vaccines have long been used against wildlife diseases, and some have now entered human trials. For some wildlife diseases, such as hantavirus in mice, transmission of recombinant vector vaccines has even been a goal. These are the basics of live attenuated vaccines and recombinant vector vaccines. Each of these transmissible vaccine designs faces its own epidemiological and evolutionary challenges. For example, there are inherent limitations on the transmission of each design. The genetic weakening of attenuated vaccines means that they do not replicate well, so they may not be able to transmit well, and certainly not transmit as well as the wild type. We're not sure whether new methods of genetic engineering can overcome this poor transmission. In contrast, recombinant vector vaccines may often transmit well, simply because they have a fully intact genome of a virus, the vector. The vector is chosen to be benign, but it will likely be transmissible, just like its wild-type counterpart. It could even be chosen to be more transmissible than the disease. Remember that the recombinant vector vaccine is a combination of a benign vector virus and a disease virus. If a benign vector virus already exists in a population, cross-immunity between the wild benign vector virus and the vaccine vector could prevent the spread of the vaccine. In other words, individuals infected with the wild vector virus may be immune to the vaccine vector virus. In addition to the challenge of cross-immunity, recombinant vector vaccines may not be as immunogenic because they only contain one or a few antigens from the wild-type disease. Live attenuated vaccines are so similar to the wild-type disease that they likely induce more complete immunity. Transmission of a vaccine does not mean that it will spread forever, but it doesn't have to spread forever to reduce disease incidence. Any vaccine transmission helps. The reduction in disease incidence depends on how transmissible the vaccine is relative to the disease. The fact that a vaccine can grow within a host or a host population means that the vaccine can evolve. Although evolution is virtually inevitable for both live attenuated vaccines and recombinant vector vaccines, its consequences differ. If attenuated vaccines are only a few mutations different from the disease virus, as is true for the current oral polio vaccine, evolution may easily and quickly revert them back to the disease. Newer methods of attenuation discussed in the paper could help reduce the likelihood of this reverse evolution. Evolution with recombinant vector vaccines is less dangerous but still potentially problematic. This is because natural selection is likely to favor the loss of the inserted antigen, generating an empty vector. Although the empty vector would be no more harmful than the natural vector, it would be likely to spread more rapidly than the engineered vaccine, potentially reducing the vaccination rate. These are just a few of the challenges facing the design and implementation of transmissible vaccines. Solutions to these problems will emerge from collaboration among evolutionary biologists, epidemiologists, and genetic engineers, and the rewards of this collaboration could be enormous. Well-designed and implemented transmissible vaccines could save lives and greatly reduce costs of ongoing vaccination programs.